Welcome! You're listening to the Uncharted Lancaster podcast, where we explore the hidden histories, forgotten places, and long-buried secrets of Lancaster County. Using modern digital storytelling tools, each episode brings a new piece of local lore to life, revealing the strange, the surprising, and the stories history left behind. Let's begin.
I want you to imagine, just for a moment, that you're out walking along a familiar riverbank.
Right, like a spot you've been to 100 times before.
Exactly. You're walking the dog, getting some fresh air. It's late summer, we're at low tide, and the water is running uncharacteristically low.
And clear?
Yeah, low and clear.
Okay.
And you're just looking out at the water, watching the current break over the river stones, when suddenly your brain does this stutter step.
Oh, I know that feeling.
Right. You notice that the rocks breaking the surface out there in the middle of the river, they aren't random.
They're not just scattered.
No, they aren't just scattered by the chaotic forces of nature. They form this massive, deliberate, geometric shape.
A V shape.
Yes, a perfect sprawling V pointing right down the center of the current.
It really is a moment of profound cognitive dissonance.
Oh, absolutely.
Because you are looking at something that has always been there, resting right under your nose, but your brain is suddenly shifting gears to see the intelligence behind it.
Yeah, it clicks.
Exactly. The chaotic scattering of nature suddenly resolves into intent. You realize it's not geology, it's architecture, submerged, ancient architecture.
And that is exactly what we are getting into today. We're doing a deep dive into an architectural mystery resting right at the bottom of the Susquehanna River.
And the rather bizarre alien-like creature it was actually built to catch.
Yes, the creature is wild. We're going to use satellite data, archaeological field reports, and even some historical paintings to completely change how you look at the water in your own backyard.
It's a fascinating stack of research today.
It really is. We're pulling from some incredible pieces today, including deep dives in the Bay Journal and Uncharted Lancaster.
Plus some really great data from the Susquehanna National Heritage Area.
Right, and field reports from the Pennsylvania Archaeology blog. Oh, and this stunning 2021 oil painting by an artist named Carol Oldenburg that really brings this all to life.
What makes this specific collection of research so compelling, I think, is how it forces us to reconsider the environments we think we know best.
Yeah, we just take them for granted.
We do. We often view rivers just as moving water, maybe a place for recreation or a geographic boundary.
Right, just a place to kayak.
But the underlying theme of all these documents is that the natural world and human history are deeply, inextricably interwoven.
Yeah.
The evidence of massive, sophisticated civilizations and these ancient ecological engines is quite literally hidden just beneath the surface of the water.
Just waiting for us to understand what we're looking at. And by the time we finish this deep dive, I promise you, you are going to look at your local landscapes completely differently.
It completely changes your perspective.
So let's start with that cognitive dissonance you mentioned earlier, standing on the riverbank and seeing that V shape.
Mm-hmm.
Our entry point into this whole world comes from a guy named Van Wagner.
Right, the environmental science teacher.
Yeah. He's a science teacher, and he actually grew up on Bald Top Mountain, which looks right down over the Susquehanna River in Pennsylvania.
It's a great vantage point.
It is. And as a kid, he would look down at the river during those low water periods we just described, and he'd spot these mysterious V shapes pointing downstream.
It's such a universal childhood experience, you know, noticing a pattern in nature and wondering if it means something.
Exactly, like finding a weird footprint.
Yeah.
But what Wagner eventually learned, and what he now actually teaches, is that these weren't natural rock formations at all.
No, they were what are known as eel weirs.
Let me just stop you there, because when I first read the term eel weir, I pictured, a modern metal grate or maybe some kind of commercial fishing net stretched across a dock.
Sure, like a modern trap.
Right. But from the drone footage Wagner eventually shot, you can see these are essentially underwater walls built entirely out of stacked river rocks.
Just massive piles of stone.
Yeah, and they rise about 3 to 5 feet off the river bottom. The two walls form a giant funnel, that V shape, pointing downstream.
It's a brilliant design.
So as fish, specifically eels, are migrating down the river, the current and these stone walls naturally funnel them into the narrow point of the V.
Right.
And right at that narrow tip, they would be trapped in woven wooden baskets or easily speared.
Think about the physics of that design for a moment. It demonstrates a profound intuitive understanding of fluid dynamics.
Oh, for sure.
And hydrologic flow. Water takes the path of least resistance, and so do the creatures traveling within it.
Yeah, they just go with the flow.
Exactly. By building these V-shaped walls, the engineers weren't trying to dam the river or fight its power.
They were harnessing it.
Right, harnessing its kinetic energy. As the river flows into the wide end of the funnel, the water is forced into a narrower and narrower channel.
Which speeds it up, right?
Yes, it accelerates the flow slightly, pushing the fish right toward the apex. It does the incredibly difficult work of gathering thousands of independent swimming creatures into a single concentrated point of harvest.
That's genius. But I really want to make sure we're conveying the sheer scale of these things to you listening.
Oh, the scale is massive.
We aren't talking about a little dam of pebbles you build in a creek as a kid on a Sunday afternoon. Wagner points out a specific site near Danville, Pennsylvania, where the weir is 1/8 of a mile to 1/4 of a mile wide at the top of the V.
That's huge.
1/4 of a mile.
To put that into perspective, that is more than 4 football fields laid end to end, spanning a rushing river.
Just imagine the back-breaking labor required to build that. You're standing waist-deep in freezing, moving water.
Without any modern equipment.
Right. You don't have cranes, you don't have diesel excavators. You are bending down, picking up wet, slippery river stones that might weigh 20, 50, or 100 pounds each.
And you're fighting the current the whole time.
And you are stacking them, lock and key, against the force of the water. And you have to move thousands of tons of this rock to build just one of these structures.
The caloric expenditure just to create the trap is staggering.
It's mind-blowing.
Which is exactly why, for decades or even centuries, these structures were largely invisible to the modern public.
Because they're underwater.
Right. Unless you had a severe drought and happened to be standing on a high vantage point like Bold Top Mountain, they just looked like natural rapids or riffles from the shoreline.
Yeah, the churning water just hides the geometry.
Exactly. But technology has completely shifted our ability to comprehend the scale of this phenomenon. The modern archaeological survey has been totally revolutionized by satellite imagery and LiDAR.
Wait, pause for a second.
Yeah.
I know what satellite imagery is, basically Google Earth. But what exactly is LiDAR?
It's a great tool.
And how is it spotting piles of submerged rocks? Doesn't water just reflect lasers?
That is a really great question. So LiDAR stands for light detection and ranging.
Okay.
Generally, it involves mounting a laser scanner on an airplane or a drone and firing millions of laser pulses at the ground to measure the exact distance to the surface.
Like radar, but with light.
Exactly. And it creates a highly detailed 3D topographic map. Now, you are correct that standard near-infrared LiDAR bounces off the surface of water.
Right. It just reflects.
But archaeologists and geologists use a specific type called bathymetric LiDAR, which uses a green laser.
A green laser?
Yeah, that green wavelength can actually penetrate the water column, bounce off the riverbed, and return to the sensor.
Oh, wow.
So they can essentially strip away the water and see the exact naked geometry of the river bottom, revealing every single stacked stone.
That is wild. It's literally like draining the river with a computer.
It really is.
And the sources detail this amazing moment during the COVID-19 pandemic involving just regular satellite imagery.
Oh, the high school assignment?
Yeah. Van Wagner, the science teacher, is stuck at home. His field trips for his Lewisburg area high school students are canceled.
Like everything was back then.
Right. So he gives them a remote assignment. Pull up Google Earth and scour the satellite imagery of the Susquehanna River looking for these telltale V-shapes.
And they found them.
They found dozens of them just sitting there in the public satellite photos, completely unhidden.
It is a beautiful example of how access to technology has democratized the archaeological survey process. Seriously, high school kids sitting in their living rooms were mapping ancient infrastructure.
And their findings align perfectly with professional academic surveys. The North Carolina Office of State Archaeology conducted a massive fish weir recording survey back in 2019.
I read about that.
Across 10 states, utilizing this kind of remote sensing data and historical records, they identified 750 of these fish weirs.
750? That's incredible.
And Pennsylvania, which might surprise some people who think of this as a purely coastal phenomenon, had the second highest concentration in the entire survey.
Wait, really?
Yeah, with 141 documented weirs.
Okay. Looking for these weirs is exactly like looking at one of those magic eye posters from the 90s.
Oh, that's a perfect analogy.
You stare at the static pattern on the river, and it just looks like noise, just random ripples. They're completely invisible until you shift your perspective.
And look from above. Right. In this case, going straight up into the sky with the satellite.
Right.
And once you finally see the V shape, your brain locks onto it. You literally can't unsee it.
It jumps out at you.
Suddenly it's everywhere. You follow the river bends on the map and boom, there's another one and another one.
The structural variations they found are just as fascinating as the sheer numbers, too. They weren't just simple, solitary V shapes.
Whoa.
No, the aerial surveys revealed complex, adaptable engineering. Sometimes they were multiple connected Vs forming a giant W, or an intricate zigzag spanning the entire width of the river. And this wasn't just to catch more fish blindly.
What was it for?
The tips of the weirs, the apexes, were constructed so they could be modular. They could be opened or closed depending on the season.
That's so smart.
They'd target fish migrating downstream toward the ocean, or alter the trap to catch different species migrating upstream toward the headwaters.
It is a highly tunable machine.
Precisely. Once you built the infrastructure, once you made that massive initial capital investment of labor to move the stones,
Which we know was a lot of labor.
right, the daily operational effort was incredibly minimal. It became a high-yield, low-energy system.
But that brings up a massive question. To understand why human beings would go through that staggering initial layer.
Moving countless tons of rock.
Yeah, to build a quarter-mile wide funnel, we really have to look at who built them, when they built them, and what kind of civilization required that much food.
Exactly.
Because you don't build a quarter-mile stone funnel in a river for a casual weekend fishing trip. You build that to feed thousands of people.
That leads us directly to the timeline and the builders. These weirs were primarily built by Native American civilizations.
Okay.
The geographic correlation is undeniable. Almost every single one of these weirs found in Pennsylvania is located adjacent to, or very near, a documented pre-contact or contact period Native American village site.
And the diet of these villages relied heavily on what they were catching. We have a master's thesis by a researcher named Alan Lutens on prehistoric fish weirs in eastern North America.
It's a key piece of research.
He notes that fish, and specifically eels, played a massive vital role in the diets of Native Americans along these rivers, well before what archaeologists call the woodland period.
Right, which stretches from 500 BC to AD 1100.
Right.
I want to pause on that term, the woodland period, because it carries a lot of weight in North American archaeology.
How so?
Generally, the woodland period is characterized by a massive cultural shift. The adoption of agriculture, the making of pottery, and the establishment of more permanent sedentary villages.
So people stopped moving around as much.
Right. Before this, populations were thought to be more nomadic, following seasonal food sources.
Okay.
But the existence of these massive weirs before the woodland period forces a paradigm shift.
Really?
Yes. It means these civilizations achieved sedentary, complex municipal societies without needing to rely on traditional terrestrial farming.
Oh, because the river was providing so much food.
Exactly. They were anchored to the river because the river, via these weirs, was providing the caloric equivalent of hundreds of acres of agricultural land.
That is an incredible way to look at it. The river was their farm, and the weir was the tractor.
That's a great way to put it.
And you can actually see the cultural footprint of this diet embedded in the very language of the region today. The linguistic evidence is hiding in plain sight, much like the weirs themselves.
Right, the place names.
Take Swatara Creek near Harrisburg. The name Swatara is derived from an indigenous language translating to where we feed on eels.
It's right there in the name.
In fact, Swatara Township actually features an eel right on its official municipal crest today.
That's amazing.
And the city of Shamokin, which drains into the Susquehanna. In the language of the Delaware tribe, Shamokin literally means Eel Creek.
The land itself holds the memory of its primary utility.
It really does.
But establishing the precise age of these structures presents a unique, almost frustrating challenge for archaeologists. The Pennsylvania Archaeology blog delves into this.
Oh, the dating problem.
Right. How do you date a pile of rocks in a river? You can't carbon date stone. A rock is millions of years old, regardless of whether a human picked it up yesterday or 10,000 years ago.
Right. If I pick up a rock from my driveway and drop it in the creek, a scientist 1,000 years from now carbon dating, that rock is just going to find out when the Earth cooled, not when I dropped it.
Exactly the problem. The rocks themselves tell you absolutely nothing about human interaction timeframes.
So what do they do?
Furthermore, the river is an incredibly dynamic, violent environment. Spring floods, massive ice flows scouring the bottom, and constant sediment movement continually dismantle and bury these structures.
So they're getting constantly messed up.
Right. They were highly likely rebuilt, modified, and repaired by multiple generations over thousands of years.
Okay, so how do we know how old they are?
To date them, archaeologists have to play a game of microscopic hide-and-seek. They have to excavate down into the mud beneath the rocks and look for organic material that was trapped within the original construction of the structure.
Like wood.
Specifically, yes, they look for the remnants of the wooden stakes that anchored the rocks in place, or fragments of the woven wooden capture baskets that were placed at the very tip of the V.
And when they actually manage to find and carbon date that wood, the results are mind-blowing.
Yeah.
Let's look at the Sebasticook Lake Fishware Complex up in Maine.
That's a famous site.
Archaeologists successfully recovered wood from a capture basket buried in the anaerobic mud there, and the radiocarbon dating placed it at 3000 BC.
3000 BC.
That is roughly 5,000 to 6,000 years ago.
Let's contextualize that time frame on a global scale.
Please.
The Great Pyramid of Giza in Egypt was built around 2500 BC.
Wow.
So these Native American engineering projects in the rivers of North America predate the Great Pyramids by 500 years.
Let's just sit with that for a second. We are trained to view ancient monumental history as something that happens in Egypt or Mesopotamia or Greece.
Always somewhere else.
Right. We think of ancient ruins as temples in the desert. But there is civic infrastructure resting in the mud behind a Pennsylvania suburb, underneath kayaks and fishing boats, that was already ancient before the first stone of the Great Pyramid was laid.
It's staggering to think about.
Van Wagner, the teacher who sparked so much of this recent local interest, firmly believes the Danville site in Pennsylvania could easily be just as ancient as the main site.
It's highly probable.
We are talking about infrastructure as old as recorded human civilization.
It shatters the reductive, often inaccurate view of early Native Americans purely as nomadic hunter-gatherers treading lightly on the earth, leaving no trace.
Yeah, this leaves a huge trace.
These weirs represent permanent, monumental municipal infrastructure. They represent a civilization engineering its environment on a massive, permanent scale to guarantee caloric security across generations.
To really visualize what this looked like at its peak, I want to bring in one of the most unique sources we have today. Yes. It's a 2021 oil painting by an artist named Carol Oldenburg titled Native Lands. It's a stunning piece of visual research.
It really captures the feeling.
Imagine you're looking down from a high bluff overlooking a wide, rushing section of the Susquehanna River in deep autumn. The trees on the banks are blazing orange and yellow.
Beautiful.
Out in the cold, gray-blue water, you don't just see one V-shape, you see an entire network of them. It's a massive W shape, spanning the entire width of the river.
Oldenburg captures the scale of human activity required to operate the system during the migration.
Yeah, you can see people in the water.
In the painting, there are figures out in the water, standing at the apexes of the weirs, actively harvesting the trapped fish from the baskets.
And boats, too.
There are small, maneuverable canoes navigating the calmer pools of water immediately behind the stone walls, ferrying the massive tetch to the shore.
And on the near bank, she paints this sprawling, palisaded village. It's surrounded by a high defensive wooden fence, and inside there are these massive, bark-covered longhouses.
It's a thriving community.
But the detail that really strikes me is the smoke. There are thick plumes of white smoke rising from multiple fires within the village. That smoke tells the real story of survival here.
That smoke represents the preservation process, which is the entire point of the endeavor.
Because you can eat it all at once.
Exactly. If you catch hundreds or thousands of pounds of eel in a matter of days during a massive migration run, you have a secondary problem: spoilage.
Right.
The Native Americans, like the Onondagas of the Iroquois Nation, whom early European colonists actually documented roasting eels at the river's headwaters.
Oh, they wrote that down.
They did. They would spend weeks smoking and drying the eel meat. Eels are incredibly calorie-dense.
They're pretty fatty, right?
They have an exceptionally high fat content compared to other freshwater fish, like bass or trout. Smoking them preserves that crucial fat and protein.
And that gets them through the winter.
turning it into a stable food source that will sustain the entire village through the brutal, freezing, barren winters of the Northeast.
And the sheer volume of food we are talking about is staggering. The Pennsylvania Fish and Boat Commission notes that historically, estimates suggest eels made up 25% of all fish biomass in the Susquehanna River basin.
25%.
1 out of every 4 pounds of fish in that entire massive, sprawling river system was an eel.
It fundamentally changes our understanding of the regional ecology. The Susquehanna wasn't just a river, it was a conveyor belt of high-density calories.
Conveyor belt, exactly.
The civilizations built on its banks were deeply attuned to the rhythms of this specific creature. But to truly appreciate the genius of the people who built these weirs, we have to understand the creature they were catching.
And it's a weird one.
Because the American eel possesses a life cycle so bizarre, so incredibly hidden, that modern scientists only fully figured it out relatively recently.
And the Native Americans had to understand this creature intimately. They knew exactly when to rebuild the traps after the spring floods, exactly when the migration would happen.
They timed it perfectly.
They synchronized their whole calendar to it. So let's talk about the target of these megastructures, the bizarre and brilliant American eel. Now, first things first, we need to clear a major misconception up right away.
I think I know what's coming.
When people hear eel, they immediately think of a giant, terrifying thing that's going to electrocute them if they touch the water.
It is an incredibly persistent myth. The electric eel, famously found in South America, is actually not a true eel at all.
Wait, really?
No, it's an entirely different order of fish, scientifically more closely related to carp and catfish.
Oh, wow. I had no idea.
The American eel, the species we are discussing, is a true eel, part of the Anguillidae family. It has absolutely no biological mechanism to generate electricity.
No electric shocks, thank goodness.
Uh-huh.
But they do have some, let's say, unique physical characteristics that make people a little squeamish.
They're not the most conventionally attractive fish.
No. The Susquehanna National Heritage Area document notes that, at first glance, people often have this visceral, almost evolutionary fear response because they look so much like snakes.
It makes sense.
It totally does. You reel in a 5-foot-long, wiggling, pure muscle tube from the river, and your reptilian brain screams, snake.
But if you bypass that initial fear response and look closely, as the researchers suggest, they have distinct fish characteristics.
Like what?
They have these small pectoral fins right behind their heads that look almost like little Dumbo ears.
Dumbo ears. That's actually kind of cute.
It softens their appearance quite a bit once you notice them. However, the other trait that turns people off is their texture.
Oh, the slime. We have to talk about the slime.
We do. They are coated in a remarkably thick, viscous layer of mucus.
Gross.
But functionally, this slime is an evolutionary marvel. It isn't just gross, it's tactical armor.
Tactical armor slime.
It serves as a physical barrier that makes it incredibly difficult for predators like birds of prey, otters, or larger fish to grip them. They literally slip right out of a heron's beak.
This is pretty handy.
Furthermore, the mucus contains potent antimicrobial properties. Because they spend so much time burrowing in the mud and sediment, they are constantly exposed to bacteria.
So it keeps them from getting sick.
The slime protects them from infections. It's their primary immune defense system.
So no electricity, little Dumbo ears, and a coat of tactical antibacterial armor slime.
That's the one.
But where the American eel goes from just weird fish to absolute biological marvel is its life cycle. The experts point out that for a very long time, this life cycle was a complete mystery to Western science because no one had ever caught a pregnant female eel in freshwater. Ever.
Which baffled biologists for centuries.
You could catch millions of them, but you'd never find eggs.
This brings us to the concept of migratory fish patterns. Most people are familiar with the migration of salmon or the American shad. Shad are what biologists call anadromous. This means they are born in freshwater rivers. They migrate out to the saltwater ocean where they spend their adult lives growing and maturing.
And then they come back.
And then they return to the freshwater rivers to spawn and lay their eggs. The American eel is the exact opposite.
They do it backwards.
They are North America's only catadromous species. They are born in the saltwater ocean, migrate thousands of miles into freshwater rivers to grow and mature, and then return to the ocean to spawn.
Hold on, let me get this straight. You're telling me an eel caught in a creek in central Pennsylvania was born in the middle of the Atlantic Ocean?
Yes.
How does a tiny freshwater fish cross the ocean without getting eaten.
Yeah.
Let's trace this journey because it is genuinely like something out of a fantasy novel.
It really is phase one.
Birth. Every single American eel on the continent is born in one specific place on Earth, the Sargasso Sea.
The Sargasso Sea is a fascinating geographical and oceanographic anomaly.
Where is that exactly?
It's located in the middle of the North Atlantic Ocean, roughly east of the Bahamas and northeast of Bermuda. What makes it unique is that it is the only sea on Earth that has no land boundaries whatsoever.
Wait, really? No coasts?
None. It is defined entirely by ocean currents. 4 massive, distinct ocean currents form a massive gyre, a slowly rotating, calm vortex of water in the center of the Atlantic.
Like a slow whirlpool.
It's named for the sargassum seaweed, a type of brown macroalgae that floats in massive, dense, tangled mats on its surface, providing a unique floating ecosystem.
So deep in this swirling, calm vortex of seaweed, the eel eggs hatch. And this takes us to phase 2. When they hatch, they don't look anything like eels.
Not at all.
For the first year of their lives, they're called leptocephalous. They're completely transparent, flattened sideways, and shaped exactly like a willow leaf.
And that shape is not an accident. It is highly specialized for oceanic drift.
How so?
At this stage, they have virtually no swimming power. They are microscopic, but their broad, flat, leaf-like shape allows them to catch the deep ocean currents, much like a sail catching the wind.
Oh, wow.
They drift passively within the Gulf Stream for thousands of miles. This journey takes roughly an entire year, slowly sweeping them northward and westward toward the eastern coast of North America.
So they're just drifting for a year.
And their transparency is their only defense mechanism in the open ocean. They are basically invisible to predators.
They're essentially tiny, transparent sails riding the ocean currents. So after a year, they finally hit the coastline and we enter phase 3.
The transformation phase.
As they approach the shallower coastal waters, they undergo a massive physical transformation. They lose the flat leaf shape and become tiny, cylindrical, transparent versions of an adult eel.
At this stage, they are called glass eels.
Because you can literally see their internal organs through their skin.
As they arrive at the estuaries and sense the freshwater outflows from rivers like the Susquehanna, a profound chemical trigger goes off.
What happens?
Their instinct drives them to turn away from the ocean and swim upstream. As they enter the brackish water, the mixture of salt and fresh, and begin actively swimming against the current, they develop pigmentation, turning gray or brown to blend in with the river bottom.
Which brings us to phase 4, the Elver stage. Wait, I have to ask about this stage. They are still small, maybe a few inches long. How do they navigate rushing rapids and massive river rocks if they're that small? Do they just swim really hard?
Swimming against a roaring rapid would exhaust and kill them. This is where their biology provides another incredible adaptation. They are incredibly determined climbers. Remember that thick mucus coat?
The slime.
They use it to essentially adhere to wet surfaces via surface tension. Because they can absorb oxygen directly through their skin as long as they stay moist, they don't even need to stay in the main water column.
Are you saying they leave the water?
They will literally slither out of the raging water and climb up wet rocks, damp moss, and the muddy edges of the riverbank, bypassing the strongest currents entirely to push deeper into the watershed.
That is horrifying, but amazing.
Yeah.
A swarm of tiny snakes climbing up the wet rocks in the dark.
It's very effective.
So they finally find a suitable habitat in a freshwater river or a small inland creek. This is phase 5. They become what biologists call yellow eels. This is their growth phase.
And this phase lasts a very long time.
Here's the crazy part. They can live in this phase completely isolated in a freshwater creek in Pennsylvania for anywhere from 2 to 40 years.
40 years.
They can grow up to 5 feet long, just hanging out under a log, eating insects, small fish, and crustaceans.
They are biding their time. The entire purpose of this decades-long freshwater phase is accumulating massive fat reserves necessary for the final, most arduous phase of their lives.
The trip back.
When specific environmental cues, which frankly marine biologists still don't fully understand, trigger them, they undergo one last dramatic transformation into silver eels.
Changes.
Their bodies thicken, their fat content peaks, even their eyes physically enlarge, adapting to see in the deep, dark ocean depths they are about to face. And they begin the massive migration back downstream in the fall.
Here is where it gets absolutely mind-blowing. The female eels at this point are carrying up to 2 million eggs inside them.
2 million.
And the journey from a creek in Pennsylvania back to the middle of the Sargasso Sea in the Atlantic Ocean is so brutally exhausting that they need every ounce of energy they can muster. So what do?
This is the craziest part.
They actually absorb their own digestive tracts for extra fuel.
It is an extreme biological process, essentially a form of programmed cell death and reabsorption.
How does a creature eat its own stomach?
Well, the energy required simply to maintain a functioning digestive system. The blood flow, the cellular turnover is immense.
So they just shut it off.
By shutting down the digestive tract completely and metabolizing those organs, they achieve two things. They free up physical space inside their body cavity to carry more of those 2 million eggs.
Oh.
And they gain a massive final calorie boost to power their muscles for a 1,000-mile swim.
It's like a spaceship deliberately burning its own life support system for fuel because it knows it's on a one-way trip.
That's exactly what it is.
They absorb their stomachs because they know they will never, ever eat again. They swim to the Sargasso Sea, they spawn, and then they die.
What's extraordinary about this from a scientific perspective is how we actually discovered it.
Oh, right, because no one had seen it happen.
Because the adults die deep in the ocean and the larvae look like transparent leaves, for centuries, no one made the connection that they were the same animal.
They thought they were two different species.
Yes. The breakthrough involved incredible historical detective work, primarily by a Danish biologist named Johannes Schmidt in the early 20th century.
What did he do?
Scientists literally had to charter boats and drag plankton nets across the Atlantic Ocean for years.
Just looking for these transparent leaves.
They would catch the transparent leaf larvae and basically play a massive game of hot and cold.
How does that work?
They measured them and mapped where the larvae got smaller and smaller, tracing them backward against the ocean currents until all the smallest specimens pointed to one location, the Sargasso Sea.
That is just an incredible piece of scientific dedication. But let's bring this back to the Native American weirs we started with, the massive stone architecture. The builders of those massive stone Vs didn't have oceanography vessels. They didn't know about the Sargasso Sea or Johannes Schmidt.
No, they didn't.
But they had such a profound observational knowledge of their local environment that they knew exactly when this invisible underwater biological clock was ticking.
They had it down to a science.
They knew that every fall, driven by cues from an ocean they'd never seen, these massive, fat-laden adults would be heading downstream on their one-way trip. And that was the exact moment to close the traps.
It speaks to a level of generational empirical science that we often fail to credit to indigenous populations.
Oh, totally.
They observed the patterns of the river with such precision that they perfectly synchronized their civilization's entire food harvest with a biological event driven by ocean currents thousands of miles away.
But this incredible journey isn't just a biological marvel or a calorie source for ancient civilizations. It turns out this bizarre, slimy, ocean-going fish is the literal lifeblood of the river's entire water quality today.
It's a crucial keystone species.
And it all relies on a completely unexpected, frankly, weird, symbiotic friendship.
Ecology is fundamentally about relationships.
Yeah.
Nothing exists in isolation.
Right.
And in the Susquehanna River ecosystem, one of the most critical relationships is between the American eel and a remarkably unassuming creature, the eastern elliptio mussel.
The eastern elliptio is the most common freshwater mussel in the Susquehanna. Now, normally when you think of mussels, you just picture a shell sitting there on the bottom of the river, half buried in the mud, filtering water.
Pretty boring, right?
Yeah, you don't think of them as active participants in an underwater taxi service. But the life cycle of this mussel is intimately, almost exclusively, tied to the American eel.
To understand why, you have to look at the mussel's primary problem, mobility.
Right, they can't swim.
Mussels are largely sedentary. If a mussel population just reproduced exactly where it sat, the local resources, the algae and nutrients in that specific spot of the river would quickly be depleted.
They'd eat themselves out of house and home.
Furthermore, the water current is always pushing things downstream. To survive as a species, they need a mechanism to distribute their young upstream against the current to colonize new territory.
So how do they move upstream?
So, over millions of years of coevolution, the eastern elliptio mussel developed a parasitic yet ultimately symbiotic relationship specifically with the eel.
How does a shell hitch a ride on a fish? When the female mussels are in the final stages of reproduction, they release these tiny microscopic larvae called glochidia into the water column.
Right.
And these larvae are looking for one very specific host: the gills of a passing American eel.
The mechanism is fascinating. When an eel swims by, displacing the water, the mussel senses the disturbance and releases the larvae.
Like a motion sensor.
Exactly. These microscopic larvae have tiny specialized hooks. When they get drawn into the eel's mouth and pass over its gills to breathe, the larvae snap shut, attaching themselves directly to the delicate filaments of the eel's gills. Now, the word parasitic sounds harmful, and the host's body does react. The eel's gill tissue actually forms a small cyst around the larva to heal the microwound,
Which covers the baby mussel.
which inadvertently completely protects the baby mussel. But in this case, the burden on the eel is minimal. It doesn't significantly harm or suffocate the fish.
So the eel just swims away.
The eel simply acts as an unwitting, armored underwater taxi. As the eel continues its determined migration upstream, climbing rocks and pushing into new creeks, it carries these encapsulated larval mussels with it.
They ride the Eel Express for about 2 to 4 weeks. And then once they've been transported miles upstream into new, uncolonized territory, they undergo a transformation.
They break out.
Yeah, they break out of the cyst, drop off the gills, settle into the riverbed mud, and grow into juvenile mussels. It is a brilliant evolutionary hack for a creature without legs or fins.
It really is. But this complex life cycle raises a terrifying ecological question. What happens when a keystone species in this chain vanishes?
Because the implications for the broader ecosystem and even human populations are massive.
To understand why, we have to look at what these mussels actually do once they settle into the mud. The eastern elliptio mussel is incredibly long-lived. They can live to be 100 years old.
100 years.
Yeah.
Just sitting on the bottom of the river, pumping water.
Pumping and filtering incessantly. A single adult eastern elliptio mussel filters up to 15 gallons of water every single day.
15 gallons a day per mussel.
They pull in murky river water, extract algae, bacteria, and suspended sediment for food, and then expel clean, clear water back into the river. They are the river's liver.
So let's look at the math here, because the numbers laid out in the research are staggering. Currently, the upper Susquehanna has a decent population of these mussels, but biologists noticed a huge problem. They're aging.
They're getting old.
They are the geriatric generation of mussels, 60, 70, 80 years old. There are very few young ones. Why? Because not enough eels are making it upstream to act as taxis for the babies.
Yeah.
If we could restore the eel population and thereby restore the mussel population to historical levels, the estimates are that 280 million elliptio mussels could filter between 2 to 6 billion gallons of water a day.
Billions of gallons every single day. In doing so, they would physically remove nearly 78 tons of suspended sediment from the water column daily.
78 tons of dirt.
Sediment is one of the absolute major contributors to poor water health. When water is clouded with sediment, sunlight can't penetrate.
Which kills the plants.
If sunlight can't penetrate, submerged aquatic vegetation dies. If the plants die, the dissolved oxygen levels crash and other fish species suffocate.
It's a chain reaction.
Sediment also carries agricultural pollutants like phosphorus and nitrogen. The mussels lock all of that away in the riverbed.
Wait, let me make sure I have this domino effect straight. If we lose the slimy snake-like fish that everyone thinks is gross,
Which we almost did.
then the 100-year-old water-filtering mussels can't have babies because they don't have a ride-up river.
Correct.
And as the old mussels die out of old age, the river water stops being filtered.
Yeah.
And because the Susquehanna River provides nearly half of all the fresh water flowing into the entire Chesapeake Bay, if the mussels go, the entire Chesapeake Bay, which is a massive economic and ecological engine itself, literally chokes on sediment.
It is the perfect illustration of an ecological cascade. We have a tendency in conservation to view ecosystems through the lens of individual charismatic species, saving the bald eagle or the dolphin.
Right, the cute ones.
But the reality is a deeply integrated mechanical network. The health of the largest estuary in the United States, the Chesapeake Bay, is functionally dependent on the gill traffic of a migratory eel hundreds of miles upstream.
That's crazy.
The formula is beautifully simple. More eels equals more mussels, which equals cleaner water for everyone.
And unfortunately, human intervention in the modern era pushed exactly that first domino, severing the connection and nearly collapsing a system that had worked flawlessly for millennia.
We really messed it up.
We established earlier that Native Americans managed this resource sustainably for thousands of years. But then, European colonists arrived.
The arrival of European colonists brought a massive shift in how the river was utilized and industrialized.
What did they do?
Initially, the colonists recognized the undeniable value of the Native American weirs. They quite literally took them over, repairing the stone walls, and eventually began building their own using similar techniques.
They just copied the homework.
The historical records cited by Lutens show settlers operating massive stone and stake weirs in rivers all along the East Coast.
Eels became an absolutely massive staple of the colonial and post-colonial diet. Van Wagner, our science teacher from the beginning, unearthed some incredible historical documents right out of his hometown of Danville.
Oh, the catch records.
He found records showing that in September of 1914 at the Danbury Weir, fishermen pulled in 3 tons of eels in just 10 days.
3 tons.
3 tons.
It wasn't just subsistence fishing. It was a major economic and cultural event. Wagner notes in his research that when word spread through the town that the fall eel migration was starting, men would literally walk off their jobs in the factories or fields to man the nets on the river.
Just abandon their jobs.
Boys would walk the streets of Danville with heavy stringers of eels slung over their backs, selling them door to door to families, restaurants, and bars. It was an absolute delicacy and a vital economic driver for these river towns.
And before we think of this as just some old-timey historical quirk like churning your own butter, the demand for eel today is still massive, but it's shifted globally.
It's a huge international market now.
The sources point out that juvenile eels, those tiny elvers coming in from the ocean, are highly prized for international aquaculture.
For sushi, right.
Yes. They are caught wild here in the U.S. and shipped live to Asia to be raised on farms for the massive sushi market, specifically for dishes like unagi, which is freshwater eel, or anago, the saltwater eel.
Because European and Asian native eel species have been so brutally overfished and their habitats destroyed, the demand for American elvers skyrocketed.
The prices are insane. In Maine, where the fishery is heavily regulated, the price for a single pound of these tiny live glass eels averaged $1,500 over a 10-year period.
$1,500 a pound, which demonstrates the immense continuous economic pressure on the species.
Oh, absolutely.
However, while overfishing is a major concern globally, the true devastating impact on the Susquehanna eel population specifically wasn't the fishermen at the weirs.
What was it?
It was the industrialization of the river itself for power generation, specifically the construction of monolithic hydroelectric dams.
This is where the story gets really tragic. The lower Susquehanna River, down near Maryland and the Pennsylvania border, is blocked by 4 massive hydroelectric dams.
And massive obstacles.
The most notorious for fish migration is the Conowingo Dam. It is a 94-foot-tall wall of solid concrete stretching nearly a mile across, and it sits just 10 miles from where the river dumps into the Chesapeake Bay.
Just 10 miles.
10 miles. It essentially shut and locked the front door to the entire massive river system for anything trying to swim up from the ocean.
The timing of the historical records highlights the slow-motion nature of this ecological collapse. You mentioned the massive 3-ton catch in Danville in 1914. Yeah. What's crucial to realize is the timeline. 1914 was actually 4 years after the Holtwood Dam, further downstream, had already completely blocked the river.
Wait, I need to do the math on that. If the dam blocked the river in 1910, stopping anything from coming up from the ocean, how were they catching tons of eels up in Danville in 1914?
Because of the eels' incredible lifespan.
Oh.
The eels they were catching in Danville in 1914, and indeed the eels that continued to be caught all the way into the 1940s and 50s, were the trapped adults.
The yellow eels.
Remember phase 5. Yellow eels can live up to 40 years in freshwater. The dams stopped the babies, the elvers, from coming up, but the adults that were already upstream were stuck.
Wow.
For decades, the fishermen were simply harvesting a doomed, aging population that had absolutely no way to replace itself. They were catching ghosts. The population was functionally extinct. It just took 40 years for the bodies to run out.
That is genuinely heartbreaking. You think the river is healthy because you were still catching fish, but you were just harvesting the remnants of a severed cycle.
Exactly.
And look, it's not like the engineers in the 20th century didn't know dams blocked fish. The government and power companies spent tens of millions of dollars building fish ladders at these dams to try and mitigate the damage.
Yeah, the fish ladders.
These are basically a series of ascending concrete pools that allow fish to jump and swim their way up and over the dam.
Yeah.
But here's the problem.
Yeah.
Those ladders were designed specifically for American shad.
Which highlights the danger of engineering a solution without fully understanding the diverse biology of the ecosystem you're trying to fix.
Yeah, shad aren't eels.
Shad and eels have completely different physical capabilities and migratory behaviors. Shad are powerful swimmers. They migrate during the daylight hours, and they possess the swimming power to fight the strong, deep mid-river flows.
So the ladders worked for them.
The fish ladders were designed to mimic that specific environment. Strong, deep daytime currents rushing down concrete steps.
But the tiny juvenile eels, the elvers, are completely different. We talked about how they climb.
Right, they slither.
They migrate almost exclusively at night to avoid predators. And because they are so small, just a few inches long, they absolutely cannot fight a main rushing current. They hug the very edges of the river, utilizing their slime to slither up wet rocks in the slow-moving shallow margins.
So a roaring, deep-water fish ladder in the middle of the river is completely 100% useless to an eel.
They can't use it at all.
They just hit the 94-foot concrete wall of the dam and stop. They pool at the bottom by the millions, unable to pass.
However, there is a modern restoration effort that addresses this biological reality. And it's surprisingly clever and remarkably simple, especially when compared to those multi-million-dollar concrete shad ladders.
Oh, the eel way.
The eel way. The sources describe this system established at the Conowingo Dam. When I read the mechanics of how this worked, I actually laughed out loud because it is so ingeniously low-tech.
It really is.
It's essentially an 18-inch wide aluminum ramp that runs from the base of the river below the dam all the way up to a holding tank at the top.
Just a little metal ram.
It's lined with a specialized textured netting, almost like artificial turfs, that gives the elvers something to grip with their mucus. And to attract them to the base of the ramp, they use a pipe that pumps just 6 gallons of water a minute down the ramp.
6 gallons a minute is barely a trickle.
It's nothing.
But to a tiny elver migrating at night, that gentle trickle perfectly mimics the slow-moving edge of a natural small stream entering the main river. It leverages their natural instincts flawlessly.
That's so smart.
The elvers sense the gentle flow in the dark. They use their natural climbing ability to scale the wet, textured ramp, and they drop right over the top into an aerated holding tank.
And it works. It works incredibly well. Once they are safely in the tank at the top of the ramp, biologists literally scoop them out with nets, put them in a specialized aerated tank on the back of a pickup truck, drive them up the highway past all 4 of the massive hydroelectric dams, and dump them back into the upper river so they can continue their journey.
It's a great stopgap.
Since 2008, they have physically trucked over 2 million eels upstream this way. In 2021 alone, they moved over 620,000 eels.
It is a phenomenal logistical achievement, and it is an absolute lifeline for the upper river ecosystem and those aging 80-year-old mussel populations we talked about.
It buys them time.
By manually reintroducing the eels, they are kickstarting that ecological engine again. However, we must acknowledge the tragic reality and the ongoing engineering challenge that this solution presents.
Yeah, there is a catch to the pickup truck method.
A massive catch. We can truck millions of juvenile eels upstream, and they will live their 20 or 30 years in the freshwater, filtering the water via the mussels, growing large and healthy.
Right.
But remember the catadromous life cycle. To spawn and create the next generation, those adults must return to the Sargasso Sea, which means that massive, 5-foot-long, egg-laden female must travel back downstream.
And the pickup truck isn't there to give her a ride back down?
No. She swims downstream, driven by that ancient instinct, and she encounters the backside of those 4 massive hydroelectric dams.
Oh, no.
Without a safe, dedicated downstream passage mechanism, these massive ancient fish are drawn by the flow of the water directly into the intake pipes, and they are pulled through the spinning hydroelectric turbines.
That's awful.
The mortality rate for large adult eels trying to pass through turbines is devastatingly high. They're simply too long to pass through the blades safely.
We took this ancient, perfectly balanced ecological machine, a biological conveyor belt so reliable that native civilizations built massive stone megastructures to harness it for 6,000 years without depleting it. And we broke it with a concrete wall.
We did.
And now our best attempt to fix it is putting a Band-Aid on it with an 18-inch wet ramp and a literal Ford pickup truck.
It's pretty humbling.
And even then, it's only a half measure because we haven't figured out how to get the adults safely back out to the ocean to actually complete the cycle.
It underscores the immense humbling difficulty of trying to replicate complex natural ecological processes with human engineering.
Yeah, we can't do it as well as nature does.
We are learning, and the eel way is a vital, necessary stopgap to keep the mussels alive and the water clean. But it highlights a fundamental truth of conservation. It is infinitely easier to sever an ecological connection than it is to rebuild one.
That really brings the massive scale of this story into focus. And that brings us to the end of our deep dive today. Let's briefly tie all these disparate threads together.
It's been quite a journey.
We started with a high school teacher looking at Google Earth and finding 6,000-year-old stone V's hiding in plain sight in the Susquehanna River, architecture older than the pyramids.
Right.
We traced the journey of the bizarre, transparent, leaf-shaped drifters catching the Gulf Stream from the Sargasso Sea, transforming into armored, slime-coated climbers that can live for 40 years in a Pennsylvania creek.
And we discovered how those fish are the vital, unwitting taxi service for 100-year-old mussels.
That literally clean the drinking water for millions of people and protect the Chesapeake Bay.
It is a profound, interwoven tapestry. It shows us how multiple generations, multiple entirely different human cultures spanning thousands of years, from the ancient builders of the Sebastopol Weirs to the boys selling eels on the streets of Danville, have interacted with and relied upon this one incredible river system.
It's amazing.
The river is not just a geographical backdrop. It is an active, living participant in human history.
So here is my challenge to you, the listener. The next time you are out walking the dog, driving over a bridge, or just looking out the window at your local rivers, creeks, or landscapes.
Try not to just see them as pretty scenery.
Exactly. Try to see them as ancient blueprints. Try to see them as the active ecological engines they are. Think about the invisible architecture resting in the mud and the complex, hidden life cycles churning away right under the surface of the water.
There is always more to learn from the landscapes we think we know best, if we just know how to look.
And before we go, I want to leave you with one final provocative thought. It's something that wasn't explicitly answered in the research we looked at today, but it's been bouncing around in my head ever since I read the mechanics of the eel's final journey.
Oh, I like this one.
We talked about how the adult female American eel absorbs her own digestive tract because her body knows she's on a one-way trip, that she will die after spawning. But think about the navigation of that trip for a second. Think about an animal that hatches in the ocean, drifts as a leaf, and then spends up to 40 years completely isolated in a freshwater river in Pennsylvania.
All alone.
She has no parents to teach her the route. She has no map. Yet, after almost half a century in the mud of a creek, she somehow knows exactly how to navigate thousands of miles back down the river out into the massive Atlantic Ocean to find one specific, shifting, floating patch of seaweed exactly where she was born.
How does she do it?
How? What if memory isn't just something we acquire through experience during our lives? What if memory is something structurally encoded, physically written deep within our very DNA, waiting half a century to be unlocked? Something to think about the next time you look out over the water and notice the geometric shapes hidden in the river stones.
Thanks for listening to this week's episode of the Uncharted Lancaster podcast. If you enjoyed the episode, be sure to subscribe and leave a rating or review wherever you listen. It really helps more people discover the show. For more fascinating local history, visit unchartedlancaster.com. And if you'd like to go deeper, check out one of Adam Zern's books at unchartedlancaster.com/books. Until next time, keep exploring.